Okay, so welcome to this next video in the playlist on group theory. In this video, what we're going to introduce is the concept of a group automorphism. Okay, so the first thing we're going to do is define what a group automorphism is actually equal to. Okay, then what we'll do is actually have a look at an example of a group automorphism to understand the definition actually in action. Then what we'll do is we'll discuss the set of all the automorphisms of a group, and we'll see how it's actually a subgroup of the symmetric group on the set that underlies the group. And then finally what we'll discuss is the concept of an inner automorphism. Okay, so firstly then, let me discuss the definition then of a group automorphism. So a group automorphism is a special type of isomorphism, and it's specifically an isomorphism of the group with itself. So let me write some of this down. So what we'll need to start off with is some arbitrary group, which we'll call capital G. So that capital G be a group then. Okay, so this is a set of symbols with a group composition law defined on it. Okay, so what then is going to be the definition of a group automorphism of this group capital G? Well, the definition of a group automorphism is that it's a function f which is going to map the group onto the group. Okay, so it's going to map elements of the group onto other elements of the group. Okay, and this is going to be a bijective map, so it's going to be a set permutation of the set that underlies the group. So it's going to relabel up all of the elements of the group with another element of the group. It's a set permutation, a bijective map. Okay, and it's going to obey the criterion to be an isomorphism. Okay, so it's going to obey the criterion that for all little g1 and little g2 are elements of the group capital G, it must be the case that f of g1 composed with g2, where this is composition in the group, is going to be equal to f of g1 composed with f of g2. Okay, and remember where this comes from. This is the criterion to be a homomorphism. It's the criterion that we saw when we were studying group isomorphisms. And remember, what it really says is that the group composition table is going to translate underneath the mapping. Okay, so what this is saying is that you pick whatever elements you like within the group. You can either compose the two of them together prior to undertaking the mapping, so compose them together in the domain here, okay, and then map the answer to what the two composed together is equal to into the codomain and get some answer within the codomain. Or you can firstly map both of them into the codomain and then compose them together in the codomain, and the answer will be the same. So mapping and composing are interchangeable with regards to the order in which you do them, basically. Okay, and we've seen that this is the criterion for a mapping to be an isomorphism. So really, a group automorphism is a special type of isomorphism. It's an isomorphism of the group onto itself, okay, rather than an isomorphism of the group onto a different group. Okay, so it's a special type of isomorphism, an isomorphism between the group and itself. Okay, so I think the best way now to proceed is to do an example, but before we do an example, let me just illustrate one example of a group automorphism that is absolutely always present. Okay, so one group automorphism that you can always come up with is just going to be the identity set permutation. Okay, so let's take the map F, which is going to map all elements of the group, so all little g within the group onto themselves. So it will map all elements of the group onto themselves. Okay, so this is the identity map from the group to itself, and it is a set permutation. It's a bijective map of the group onto itself, and this is going to obey this isomorphism criterion here. Okay, because quite simply, for whatever little g1 and little g2 we pick from within the group, if we consider what is f of g1 composed with g2, the answer there will just equal g1 composed with g2, because f is the identity map, so it'll just map g1 composed with g2 onto g1 composed with g2. Okay, so that's what the left-hand side will be if we're using this mapping here. The right-hand side here, f of g1, that will just equal g1, again, same reason, we're dealing with the identity map. g2, when we take f of g2 here, we'll again just get g2, so here we'll be composing g1 with g2, where this is composition in the group, and I should stress that, usually when we have the isomorphism criterion, the composition here is different to the composition here. This is composition in the domain group, and this is composition in the codomain group. However, in this case, the domain and codomain groups are exactly the same, so the composition is the same basically. This is composition in the group, and this is also composition in the group. Okay, so because we're only working with a single group here, those two compositions must be exactly the same. Okay, right, so indeed we've got G1 composed with G2 in the group on the left hand side, and we've got G1 composed with G2 in the group on the right hand side, so of course these two things are equal to one another, and that then implies that these two things would be equal to each other. So for any group, the identity map, which just sends all of the elements of the group onto themselves, that is always a group automorphism. Okay, it's not a very interesting example of a group automorphism, but it is a group automorphism. Okay, so what I now want to give you is a more interesting example of a group automorphism, okay, to motivate further discussion of group automorphisms and give you some insight into what this really means and why this is such a powerful concept. Okay, right, because at the moment you might be thinking, why should I care? But we will see what a powerful concept this is when we come on to the example. Now, just before I do the example, what I want to point out is the fact that if you've got an automorphism, a group automorphism of the group capital G, it must always map the identity element of the group onto the identity element. And this is because, after all, this is a group isomorphism. Okay, it's a very special group isomorphism because it's between the group and itself, okay? But it's still a mapping of a group onto another group, which is a bijective mapping, and it must obey this criterion. So this is an isomorphism, and we know whenever we have an isomorphism that the isomorphism must map the identity in the domain onto the identity in the codomain. Okay, this criterion here makes this absolutely necessary. Okay, if it weren't the case that the mapping maps the identity onto the identity in the codomain, okay, then this criterion couldn't possibly be satisfied. Now, what this means in the case of group automorphisms is that the group automorphism will always map the identity element of the group onto the identity element of the group. So f of the identity is always going to equal the identity, okay? And I think that's an important point to point out just before we actually do an example of a non-trivial group automorphism. Okay, so our first example then of a non-trivial group automorphism. Okay, so because it's going to be non-trivial, and because this is our first example, I want to use a very, very simple group, okay, to actually work in. It also means I can draw the group out and we can get a very good understanding of it. But I don't want it to be so trivial that it's meaningless. So I've got a good group to work with, and the group that we're going to work with is the cyclic group on the set of free elements, C3. This is going to be small enough that it's easy to understand, but big enough that we actually get a non-trivial example. Okay, right, so the cyclic group on the set of free elements. Just before we actually launch into the automorphism that I've got on this group, let me just remind you of this group. Okay, so remember, the way that you can think of this group, the construction of this group, is you firstly take the set containing free elements. So we've got the set here containing the numbers 1, 2 and 3. Okay, so it's got 3 symbols in here. Okay, and then what you're going to do is you're going to imagine all the cyclic set permutations of this set of free elements, and it's those cyclic set permutations of this set of free elements that are going to be the elements of C3. Okay, so firstly let's just think about what are the free cyclic set permutations of this set of free elements. Okay, so let me just draw this out. So here we'll have our set, and here's a duplicate of our set, and now I can draw out some set permutation here. So one of the cyclic set permutations is the one that maps all elements onto themselves. So it maps 1 onto 1, 2 onto 2, and 3 onto 3. This is the identity set permutation, and this is a cyclic set permutation. And I suppose I should have probably just reminded you of what I mean by cyclic set permutation. So a cyclic set permutation is one that can be interpreted as moving all elements of the set along by a certain amount. So this is a cyclic set permutation because this is the set permutation that really moves everything along by nothing. Okay, so we will call this element the identity. Okay, and you could imagine actually putting this into your set that's going to form the group, if you like. You could imagine actually putting this great big symbol, which actually is a little drawing of the set permutation, into the set that's going to form C3. But to make it simpler, we'll just denote this element by this simpler symbol here, which is the identity symbol. Okay, right, now let's have another cyclic set permutation of this set of free elements. So again, I'll draw out my set of free elements twice, and now what I want is the cyclic set permutation that's going to move everything along by 1. Okay, so it's going to send 1 to 2, okay, 2 to 3, and 3 then back to 1, because obviously there's nothing left for 3 to go on to, so we'll have to redouble back on ourselves. Okay, so here is the next cyclic set permutation of this set of free elements. Okay, and again we could imagine actually putting this as the symbol that we're going to put into our set that's going to form the group, but instead we will have a simpler symbol to denote it, and the symbol we'll use will be sigma here. Okay, then there's one final cyclic set permutation of this set of free elements, and that corresponds to moving everything along by 2. Okay, so once again I'll draw out my set twice, and now I'm going to move everything along by 2. So 1 this time is going to go on to 3, okay, 2 would go on to 4, but there is no 4, so we'll have to double back and we'll go on to 1. So 2 will be sent on to 1, and 3 will then be sent on to 2. Okay, so here is the cyclic set permutation that corresponds to moving everything along by 2. Okay, and we'll denote this cyclic set permutation by sigma squared, because it is just sigma composed with itself, basically. So sigma composed with sigma will make this one, because sigma composed with sigma will correspond overall to moving along by 2, because you'll move along by 1 but twice. Okay, so that's a useful way of notating this element. So we'll have this sigma squared, and this one is sigma here. Okay, so then what you do to construct C3 is you put all of these elements into a set, and as I say, you could either imagine actually putting these pictures into the set, and those would be the elements of the set, but they're quite complicated symbols, so instead we'll use these symbols here. So we'll have the identity, sigma, and sigma squared, and that's going to form the set that's going to underlie our group C3. Okay, right. Now at the moment that's just a set. Of course, to turn it into a group we need to actually have a group composition law. Okay, so we need a way of composing all of the elements here together, and of course the way we'll do this is just through the composition of the set permutations here. Okay, and that is actually going to form a group composition table. So let me draw this out here. So we'll call our composition just abstract composition here. Okay, I'll give all of the elements of the group a column. So the identity's got a column, sigma's got a column, sigma squared's got a column. Okay, and then we'll give all of the elements of row as well, the identity, sigma, and sigma squared. Okay, and I'll colour this in purple to match the set. Okay, and now what we want to do is define what all of the elements composed together is actually going to be equal to, and I've said the way we're going to do this is just through the composition of the set permutations. Okay, so the identity composed with the identity is obviously just going to be equal to the identity. If you do this one twice, you will end up still with the identity. Everything will be sent onto itself. Okay, and indeed the identity composed with any other set permutation is just going to leave that set permutation unchanged. So the identity composed with sigma will be sigma. The identity composed with sigma squared will equal sigma squared. Then when we do it the other way around, so sigma composed with the identity, okay, that means do the identity first and now do sigma. Again, that will overall just be the same as doing sigma. And then sigma squared composed with the identity, again, that's sigma squared. So those are the trivial entries in the composition table. Now let's do the 4 non-trivial ones. So when we compose sigma with sigma, we already know, I've already discussed what that's going to equal. We are effectively moving everything along by 1, but twice, so that will be the same as moving everything along twice, okay, by 2, so sigma squared here, okay. Then if we do sigma composed with sigma squared, that will mean firstly do sigma squared and then do sigma, so move everything along by 2, then move everything along by 1, and that's the same as moving everything along by 3. Now what does it mean to move everything along by 3? Well, let's just think about this. When we moved everything along by nothing, 1 went on to 1. When we moved everything along by 1, 1 went on to 2. When we moved everything along by 2, 1 went on to 3. When we move everything along by 3, where's 1 going to end up being sent to? Well, it's going to be sent back to 1. So in fact, you'll end up back with the identity set permutation here. So sigma composed with sigma squared is actually going to equal the identity. Okay, right. Now sigma squared composed with sigma, well, that's the same thing as sigma composed with sigma squared. You've just done them in the opposite order. This says now firstly move everything along by 1, then move everything along by 2. Again, we'll end up moving everything along by 3, which is equal to the identity. Then finally, sigma squared composed with sigma squared, so move things along by 2 twice. Okay, so that's the same as moving everything along by 4. So we've just discussed that when we move everything along by 3, 1 will be sent back to 1. When we move everything along by 4, 1 will be sent back to 2. So that will be the same actually as sigma. Okay, so the answer here is going to be sigma. Okay, so there is our cyclic group on the set of 3 elements. Okay, it's got 3 elements itself. Okay, and here is its group composition table, and this does obey the axioms of group theory. It's closed, it obeys associativity, it has an identity element, and it has inverses. Okay, right. So what I now want to show you then is an example of a non-trivial automorphism, group automorphism, on this cyclic group on the set of 3 elements. Okay, so firstly let me define it, and then I'll show you how it's actually going to be a group automorphism. Okay, right. So I'll actually draw it out for you here. So let's have our set C3 denoted in the typical blob fashion. Okay, so C3 is here with the identity sigma and sigma squared in it. Okay, and I'll give it a bit of colour on here. So we've denoted C3 in green, and I'll denote it once again in green here. Okay, and now we're going to have a mapping, a relabeling mapping, a set permutation of C3, and I'm going to draw it here. So here again is C3. This now is going to be the codomain C3. Again, I'll outline it in green, and I'll stick all the elements there. So I'll have the identity, sigma, and sigma squared. Now we know that one group automorphism will just be the identity set permutation, which will send all elements of the group onto itself. Okay, but I want to show you the non-trivial group automorphism, and there is only one possible set permutation that is even plausible. Okay, because what do we know? The identity has to be sent to the identity always. Okay, we've just discussed that. So there's no ifs, no buts, there's no sort of like negotiation available there. The identity always goes on to the identity. Okay, now we don't want this overall to be the identity set permutation, so we don't want sigma to go on to sigma, because then this would just be the identity permutation. So the only thing that's left over to us is to swap sigma and sigma squared around. So send sigma onto sigma squared and sigma squared onto sigma. Okay, so that then is going to be what I am going to claim is a group automorphism, and an example of a non-trivial group automorphism. So this is my F. Okay, now So it is a set permutation, so it's a nice bijective map of this group onto itself. Okay, what I now need to prove is that it obeys this criterion, and remember what this criterion really actually means. It means that if you relabel up the group composition table according to this relabeling map, you will end up with the same group composition table as the codomain. Okay, now in this case, our codomain is actually our group itself, so we need to be able to relabel up our composition table according to this relabeling map and get the same thing back again. That's what it means to be a group automorphism. Okay, so I'll say it again because that's a really, really important point. Okay, to be a group automorphism, you need to be this relabeling map, this set permutation of the set that underlies the group, which we've got a picture of one here. Okay, and you have to be special because when you apply this relabeling map to the entire composition table, it has to be the case that the overall end product of relabeling up the composition table is the same, i.e. if you use the end product to work out what any two elements of the group composed together is equal to, it will give you the exact same answer as before, basically, and that's what really this is saying. Okay, it's saying that if you compose them together in the original composition table and then relabel it, okay, it's the same as if you firstly relabel them and then compose them together, and that's really capturing the fact that when you relabel this composition table, you get the same thing back again. Okay, right, so let me now apply this relabeling map here to my composition table and show you that the end product is actually the same thing. Okay, so I'm now going to relabel up this composition table here. So I'll colour this in orange now. So this is my relabeled up composition table according to this relabeling map that I've got over here. Okay, so I'm going to call it composition once again. So now I'm just going to go through and relabel up everything here. So the identity, what do I relabel that up with? I relabel that up with the identity because the identity is being sent to the identity. Sigma, I relabel that up with sigma squared. So I relabel this one sigma squared here. Okay, sigma squared here, what do I relabel that up as? I relabel that up as sigma. The identity over here, I relabel that up as the identity again. Sigma, I'll relabel that up as sigma squared, and sigma squared, I'll relabel that up as sigma. Okay, now I have to go through and relabel up these portions as well. Okay, so the identity, I'll relabel that up as the identity. Sigma, I'll relabel that up as sigma squared. Sigma squared, I'll relabel that up as sigma. Sigma, I'll relabel that up as sigma squared. Sigma squared, I'll relabel that up as sigma. The identity, I'll relabel that up as the identity. Sigma squared, I'll relabel that up as sigma. The identity, I'll relabel that up as the identity. And sigma here, I'll relabel that up as sigma squared. Okay, right, so there is my relabeled composition table, and I claim that this composition table is actually the same as this composition table. Now you might be thinking, well, that doesn't look like that. Okay, but the reason that this does not look like this is because, look, the order that I have put elements up here and down here is different to the order that I've put them up here and down here. Okay, so the way that I have ascribed elements of the group, columns and rows in the composition table, is different here than it is here. That is the reason that these two look different. As composition laws, these are exactly equal to one another, and what I mean by that is that if you take any two elements in here, okay, so take any two elements of your set and compose them together in this one, the answer is identical as to what you would get if you used this one. Okay, and what I'm going to do now is I'm going to show that if I just change the order in which I do this, okay, so I'm going to now give sigma this column back again, and I'm going to give sigma squared this column, and the same with the rows down here, I can turn this one into looking identical to this one. So what I'm saying basically is these look different, but they're not different. Okay, so let me just rewrite this one in a different way and turn it into looking identical to that to convince you that these two are the same. Okay, so I'm now just going to swap these two around. I'm going to say we're going to move this column into this position, and we're going to move this column into this position, and the same with the rows. So we'll put it now in this order. Okay, but the actual answers to what two things composed together is going to be equal to, I'm going to put the exact same answers as what I have here. Okay, so I'll colour this again in orange to denote the fact that this is going to be identical to this one, just written in a different way. And I want to stress that when I do this, I'm just writing it in a different way. I'm not changing the composition law at all. I'm just writing it in a different way. I'm presenting it in a different way. Okay, so the identity composed with identity, and here is the identity. The identity composed with sigma squared is equal to sigma squared. The identity composed with sigma is equal to sigma. Sigma squared composed with the identity is sigma squared. Sigma squared composed with sigma squared is equal to sigma. Sigma squared composed with sigma is equal to, whoops, nearly made a mistake there, the identity. Okay, sigma composed with the identity is equal to sigma. Sigma composed with sigma squared is equal to the identity, that's over there, and sigma composed with sigma is equal to sigma squared. And hopefully you can see that that now is identical to that one. Okay, so here's the powerful thing. What I have done is I have relabeled up the elements of the group, okay, and relabeled up the composition table according to this relabeling map. And I've ended up with the exact same composition table, okay? So what is this doing? What does this actually mean? Okay, what is this capturing? This is capturing an incredible symmetry in the structure of the group. Sigma and sigma squared, these are different elements in the group. They have different symbols in the group, but their algebraic structure in the group is identical. So identical that if I swap them round, if I say, okay, I don't want to call sigma sigma anymore, I want to call it sigma squared, and if I swap sigma squared around and say, no, I want to call this sigma now, if I swap those symbols around, okay, the group is still identical. So all that's different between these two elements, essentially, is that they've got different symbols. Their algebraic structure in the group is identical, okay? And that's what this is really all about. Group automorphisms are capturing these beautiful patterns in the structure of the group, okay? It's showing us, it's illustrating to us these elements that are effectively identical algebraically. Okay, it's showing us the algebraic symmetries of the group. That is the way of saying it well. Okay, it's showing us the algebraic symmetries of the group. So group automorphisms correspond to algebraic symmetries of the group. Okay, and I hope you are starting to get some intuition as to what these actually mean. Okay, so we'll have a break here, and in the next video what we'll talk about is the set of all automorphisms of a group.